We will start by 610. Hello and welcome to the course of Introduction to Semiconductor Devices. This is the live problem solving session for the third week of the course, which is being taught by Professor Naresh Kumar Imani from IIT Hyderabad. The course code is NOC25E92. So, something about me. My name is Mayank Goel, and I am a research scholar at the Department of Electrical Engineering at IIT Bombay. And about the course. So it's being taught by Professor Naresh Kumar Imani, who is an associate professor at Electric Department of Electrical Engineering, IIT Hyderabad. So co- pl- the course plan for third week is thermal motion of carriers, carriers under electric field, mobility and drift current, diffusion of carriers, general expression for current in a semiconductor, energy bands under electric fields, etc. So this problem solving session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we'll do a recap of the lectures for week 3. So this is the course recap provided by Professor Naresh Kumar Imani. So first is interpretation of energy band diagram. So when an electric field exists inside a material or applied as an external stimuli, the band energies EC and EV become a function of position. So they are not constant throughout the semiconductor. They change as as a function of position, and their values then become dependent on the direction and magnitude of the electric field, and this is called band bending. And by studying the band bending, you can also figure out the electric field that is being applied, or that is present inside the material. You can figure out the electrostatic potential, the kinetic energy, and the potential energy of the carriers, the carrier density N and P, just by visualizing EC and EV as a function of position. So these are the formulas that you can get from the values of EC and EV. So let's assume there's a char- particle with a minus q charge. So the potential energy for that will be minus qv, and that is EC minus E reference, and E reference is your the Fermi level energy. So the by changing this, you can get the electrostatic potential V equals to minus 1 by Q EC minus E ref, and the electric field is then given as 1 by Q del of EC by del X, which is 1 by Q del EV by del X, or 1 by Q del EI by del X. So any of the bands you can take the derivative with position and you can get the electric field. Next, minority carrier diffusion equation. Diffusion is migration from regions of high particle concentration to regions of low particle concentration due to random thermal motion of carriers. So if you have one region where the concentration of particles is high and another region where the concentration of particles is low, then due to thermal motion of carriers, there will be movement of particles from high concentration to the lower concentration so that it will try to equalize the concentration, and this is called diffusion. The minority carrier diffusion equation is a partial differential equation in space and time depicting the evolution of carrier action when a semiconductor system is perturbed. So and at equilibrium, the a semiconductor is has a constant particle concentration throughout, but if you perturb it so that in some regions there is a higher particle concentration and in other region there is lower particle concentration, then the then the particles will try to equalize themselves, and equation is governed by the minority, that motion is motion of carriers is governed by the minority carrier diffusion equation, which gives the which gives how the particles are how the particles will move, will diffuse with respect to both the position and time. So it is derived from continuity equations under the following assumptions. System under analysis is one dimensional, so we only consider one dimensional system to for our ease of understanding. If we consider two dimensional or three dimensional systems, then it becomes very complicated. Analysis is restricted to minority carriers, so we only consider the movement of minority carriers and not the majority carriers. Electric field is almost equal to zero in the semiconductor, so we assume that there is no applied electric field. Perturbation is mostly the photo generation of carriers. So generally we assume that the perturbation that we have given is by photo generation. So we shine light and generates that generates electron pairs, and then we turn off the light and we let the system come back to rest. Low level injection conditions prevails, that is delta P is very less than N naught for N type semiconductor, or delta N is less than P naught for P type semiconductor. So what low level injections means is it does not, so that means it that the excess particles generated, excess carriers injected do not change the do not change minority carriers into majority carriers or majority carriers into minority carriers. That is, if that for n-type semiconductor, the majority carriers are n-type and are electrons, and electrons n naught, and minority carriers are holes p naught. So delta p should be less than n naught, so that the holes remain the minority carriers. Similarly, for p-type semiconductor, the electrons should remain the minority carriers even after a carrier injection. So that is called low level injection. So under these assumptions, the minority carrier diffusion equation for electrons in p-type materials or holes in n-type materials is given as these: del 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 of delta np by del t is equals to dn delta square delta np del square delta np by del x square minus delta np by tau n plus gl. This is for electrons in p-type materials. Del delta pn by del t equals to dp del square delta pn by del x square minus delta pn by tau p plus gl. This is for holes in n-type materials. So we can further reduce this complexity of these equations by applying additional simplifications depending on the conditions that we are given. So dn is your diffusion constant and tau n is your relaxation constant. Time to time take average time taken by the particles to come to equilibrium, and gl is your the amount of photocarriers generated. Next is minority carrier diffusion lengths. The diffusion length wherein excess carrier concentration falls off exponentially to 1 by E of to that at the point of injection is termed as mitotic carrier diffusion length. It is given as so diffusion length is if if I perturb the system at point A, I inject electrons at point A, and so and so at point B is at lower concentration, so the electrons will move from point A to point B. But since they are moving through a lattice, they will they will keep losing energy, and they will stop in the middle. So diffusion length is if the carrier if when the carrier concentration is moving from point A to point B, the carriers are moving from point A to point B. The excess carrier concentration is drastically decreasing, and the point at which it becomes 1 by E of the original carrier concentration, that is the carrier concentration at point A, that point is called a diffusion length. And for holes, it is LP equals to square root of dp tau p, and for electrons it is ln square equals to square root of dn tau n. So you can also say that LP or ln is the average distance a hole or electron diffuses before recombining. So at some point they will the excess electron hole pair generated will recombine, and that is what is called diffusion length, the distance traveled till that point. And this is quasi-Fermi levels. So quasi-Fermi levels are energy levels used to specify the carrier concentration inside a semiconductor under non-equilibrium conditions. So at equilibrium condition, there will be one single Fermi level, but in non-equilibrium condition, when there's a difference of electrons, difference of carrier charge particle, difference of carrier concentration for the semiconductor, so you will have multiple Fermi levels because of that. So if and that is given as quasi Fermi levels because they will be constantly changing with time to come back to equilibrium. By definition, they are related to the non-equilibrium carrier concentration in the same way EF is related to the equilibrium carrier concentration. So our Fermi level is related to equilibrium. Quasi Fermi levels are related to non-equilibrium. EFN, which is a quasi Fermi level for electrons, and EFP, which is a quasi Fermi level for holes, are given by the equation EFN equals to EI plus K tau ln n by Ni, and EFP equals to EI minus KT ln P by Ni. So this is the same equations that you use to calculate the Fermi level. Similarly, for quasi-Fermi levels, the equation remains similar, but here the N and P are non-equilibrium carrier concentrations instead of being the equilibrium carrier concentrations. So recap of last week. Last week we had studied the impact of temperature on Fermi level, carrier drift, mobility, resistivity, charge neutrality relationship, and semiconductor in electric field. We had studied that the drift current density is given as E n mu n plus p mu p uh, into applied electric field, where mu and mu p are mobilities, and these are the some standard values for mobility. And we also studied how the electron hole pair is generated. So in case of a semiconductor and electric field, the holes will move in the direction opposite to the direction of electrons will move in the direction of electric field, and holes will move opposite to the direction of electric field. So let's take this semiconductor where x0 and xl are the boundaries. So let's assume that the electron is at rest at x equals to L, and it starts moving towards x equals to 0 in the due to the electric field. Then you can see at x equals to L, this is how the EC is here and EV is here. But as it goes towards x equals to 0, the kinetic electron is moving, so the kinetic energy of the electron is increasing. So EC moves down and the excess energy is gone towards the kinetic energy of the electron. Similarly, for holes, it is at we consider it at rest at x equal to L, x equal to 0, and x as it goes towards x equal to L, it gains kinetic energy, and that kinetic energy is reflected in the shift in EV. So we can say that kinetic energy is proportional to the electric field, that and therefore the electric field is given as 1 by E dEc by dx, or 1 by E dEv by dx, or 1 by E di by dx. Anything is the same. So so here you are given a band diagram where at one point the Eg is smaller, but at another point Eg is larger. So this is not a correct band diagram. As you can see here, with electric field, the change in EC and EV will be in the same direction, not in the opposite direction. So your band gap will remain constant with respect to applied electric field. Your electric field does not change your band gap. So you have a hypothetical band diagram here where from 0 to L by 4 you have a changing band diagram. From L by 4 to 3 L by 4 your uh, bands are constant, and then again from 3L by 4 to L their bands are changing. So if you have to plot the electric field, how will you plot? You will just divide the you will just do del EC by del X. So if you do del EC by del X here, you will get some negative value. So your electric field will be some negative value here. In the middle range, your del EC by del X will be 0 because the EC is constant. So in the middle range, your electric field is 0, and then again from in the last region, your del EC by del X will be negative, and the slope is same in both cases. So your the slope will be same as earlier. So your potential energy is given as EC minus E ref, where E ref is your Fermi level. So your Fermi level is constant like this. So if you subtract it, you will get your potential energy like this, and the kinetic, since the total energy is conserved, your kinetic energy will then look like this. So from your band diagram, but band position versus your semiconductor position, you can calculate your electric field, kinetic energy, potential energy, as well as electrostatic potential. Next up is diffusion of carriers. So let's assume that in this region you have access to acceptor ions 10 raised to power 16, and this region your this is an intrinsic region where your n equals to p equals to ni equals to 10 power 10. So here you have p into p holes 10 power 16 and electrons 10 power 4. Here both are 10 power 10. So because of that you will have you have excess of so you have 10 power 16 holes here, 10 power 10 holes here. So there's a concentration gap. So holes will diffuse into this region. Similarly, you have electrons 10 per 10 here, and electrons 10 per 4 here. So electrons will diffuse into this region, and then you can calculate the diffusion diffusion values. So this is the calculation of diffusion current density. J and J and diffusion will be E Tn dn by del n by del x, and for holes it will be minus E dp del p by del x, where dn and dp are diffusion constants. So total current density will then be the sum of drift current and diffusion current. So Jn would be your E n mu n E electric field plus E dn del L by del x, and Jp will be P mu P E into electric field minus E dp del P by del x. And in the case of 3D, this will be instead of del n by del x, you will have Laplace 3D Laplacian del n, and this will be del p, Laplacian n, Laplacian p. So at equilibrium, you will have Jn equals to Jp, because at an equilibrium there will be the net current will be zero. So Jn will be equal to Jp. So you will have all these terms equals to zero, and from there you can calculate dn by mu n equals to kt by q. This is called Einstein's relationship. From here you can calculate the diffusion coefficient as in terms of mobility, and you can also calculate del n by del x in terms of electric field using the formula. So you have n equals to ni exponential ef minus ei by kt. You take the derivative, it becomes n by kt minus dei by dx. You multiply by you do the electric. You multiply both sides by charge, so this becomes electric field. So this becomes del n by del x equals to minus n q by kt into electric field. Next is non-uniform doping. So in case if you have a semiconductor where it is been doped non-uniformly, so you don't have to apply an external electric field. There will be a built-in electric field inside due to the non-uniformity of doping. So let's assume the doping concentration changes with position as Ni exponential EF minus EI x by kt. So the electrons will diffuse in this case, and this will lead to change in fixed charge. So a built-in electric field will be created, which opposes the diffusion till equilibrium is reached. So you have EF from here you can say EF minus EI equals to KT ln ND by NI. So let's say you have two regions, one where N is high and another where N is low. So you have diffusion of electrons from here to here, but there's no external field, so there should be no diffusion. So there will be an built-in electric field that opposes this diffusion, so that the net diffusion is net change in concentration is zero. So then del EI by del X is minus KT NI by ND dot 1 by NI del ND by del X dx. So which is so del EI by del X is equal to minus KT by ND dND by dx. So this gives your electric field, which is electric field equals to 1 by Q del EI by del X, which is equal to minus KT by Q 1 by ND del ND by del X. If you have uniform doping, your del ND by del X will be zero. So your electric field will be zero. So there will be no built-in electric field in uniform doping. But in case of non-uniform doping, your built-in electric field will be given by this equation. And then how the band diagram will look like for non-uniform doping. So it will look like this. So at this point, your electron concentration is high, so your Fermi level is closer to EV. Your Fermi level is closer to EC. Here your electron concentration is low, so Fermi level is farther from EC. You can see you have a uniform Fermi level, which is how it should look in an equilibrium condition. So in equilibrium, your Fermi level will be constant. It only in the non-equilibrium case you will have a varying Fermi level. So you have an example here. Assume the donor concentration in an N-type semiconductor at T equals to 300 Kelvin is given by ND of X equals to 10 power 16 e power minus x by L, where L equals to 2 into 10 to the power minus 2 centimeter. Determine the induced electric field in the semiconductor at x equals to 0 and x equals to 10 power minus 2 centimeter. So if you do dNd by dx, you will get 10 power 16 e power minus x by L into minus 1 by L. So the electric field will then be KT by Q into 1 by L. And then you can put just your KT for 300K is 0.0259. Your L is 2 into 10 to minus 2. So that will what you will get. And so you don't have to put Q. If you take it assume it in terms of electron volt. So it will come out to be around 1.3 volt per centimeter. At this is at x equals to 0. So now let's come to another example, another analysis of band diagram. So you have another hypothetical band diagram. So your Fermi level is Eg by 3 from the conduction band, and then for at some after some time it drops very close to the your EC drops very close to the Fermi band, then moves back up. So if we have to calculate the electric, so first question is the semiconductor in equilibrium? This the so you can see the Fermi level is constant, so the semiconductor is in equilibrium. Now you have to calculate the electric field in this region. So you can see here the band is constant, so electric field is zero. Here the del EC by del x will have a negative slope, so you have a negative electric field. Here del EC by del x has a positive slope, so you have a positive electric field, and then again it becomes zero. So you can see it's zero, then negative, then positive, then again zero. Next is kinetic energy and potential of electrons and holes identified by numbers 1, 2, and 3. So for holes 1, 2, and 3 are here, and electrons 1, 2, and 3 are here. So if the point is on the band, then your kinetic energy is zero because it's in equilibrium. So the band, so the electrons there are at an equilibrium, so they are not moving. And the potential energy is given as EC minus E ref, where E ref is your Fermi level. So at point 1, your kinetic energy will be zero because the point is on the band. On the band, at point 2, your kinetic energy will be this gap, which is Eg by 3, and your potential energy is given by your EC minus EF, which is almost zero. So potential energy is zero, and at point 3, your kinetic energy is zero because it's lying on the band, and your potential energy is also zero because EC is almost touching EF. For hole, and so similarly for holes cases, you can calculate. So we are studying equilibrium versus non-equilibrium conditions. So uh, so under thermal equilibrium, you have electron hole pair generation and electron hole pair recombination, which are going at the same rate as it's in thermal equilibrium. So in case of intrinsic semiconductor, you have equal number of electron and hole concentration, N naught equals to P naught equals to Ni. Whereas for an n-type semiconductor, your N naught is given as a N naught is given as your donor concentration. P naught is given as your Ni square by Nd, and N naught P, which is N naught P naught equals to Ni square. So So due to doping, your equilibrium is shifted now, but it is still in equilibrium. So are the electrons and holes frozen in their respective bands of equilibrium? That is not true. So it's a dynamic process. So there is thermal generation and recombination going on, but it is going on at the same rate. So they're not frozen, but they the they are constantly changing, but the overall concentration is not changing. Whereas in non-equilibrium, the equilibrium is shifted by external stimulus, that is, you apply an electrical stimulus or an optical stimulus such that the concentration changes, concentration is put out, and the formula NP is then not equals to NP does not is not equal to Ni square in non-equilibrium condition. So excess carrier generation and recombination. So if we apply light to light to a semiconductor, it will generate excess. It will generate excess electron hole pairs. That excess is called excess generated electron hole pairs are called del n, delta n, and delta p. And uh, after some diffusion, they will so due to that excess generation, they will diffuse into the semiconductor, and after some time, they will recombine. So let's say light creates an excess of 10 per 16 10 per 16 electrons per centimeter cube per second. So your original N naught was 10 per 15, and so original P naught was 10 per 5. If we consider Ni is 10 per 10, the new N is N naught plus del N, which is 10 per 15 plus 10 per 16. That is 1.5 into 10 raised to power 16 per centimeter cube. Your excess holes are P naught plus new holes are P naught plus new hole density is P naught plus delta P. It is 10 per 5 plus 10 per 16. That is 10 per 16 per centimeter cube. So now if you calculate NP, it becomes 1.1 10 per 16 into 10 per 16. That is 1.1 10 per 32, and that is very different. That is very very large compared to Ni square, which is 10 per 20. Now if you turn off light, so this excess this new carrier density will try to regain the old carrier density, that is 10 per 15 and 10 per 5. So which carriers, majority and minority, determine the rate of recombination. So N has to go from 1.1 to 10 per 16 to 10 per 15, but P has to go from 10 per 16 to 10 per 5, which is a very large difference. So the so the rate will be determined by del by P. It has to go from 10 per 16, then to 10 per 10, then to 10 per 5. So at t equals to 0, your delta P is 10 per 16. So we assume that it reaches equilibrium at infinite time. So at t equals to infinity, it will reach 10 per 5. And at what point delta P is equals to Ni, that is given as t equals to T naught. So minority carrier concentration determines non-equilibrium dynamics. So this is called high level injection because here the minority carrier does not remain a minority carrier anymore, as it has exceeded as the injected carriers were more than the initial excess carriers, initial carrier concentration of N naught. So we will be using the formulas N naught P naught, which is the electron hole carrier concentration as a thermal equilibrium. N and P are electron and hole carrier concentrations at a given point of time. Does not matter at equilibrium or non-equilibrium. So then delta N is given as N minus N naught. and delta P is given as P minus P naught. So these are the excess carrier concentrations. Gn and Gp is the generation rates for these excess carriers. Then tau and tau P are the lifetimes for this minority carriers. So tau n is given as minority carrier lifetime for electrons in p-type material, and tau p is minority carrier lifetime for holes in n-type materials. So n naught and p naught will be independent of time and position as they are the equilibrium values. So for position, only in case of uniform doping they are independent. So if we have uniform doping, then n naught and p naught are independent of position. In case of non-uniform doping, they will be dependent on position, which will be determined by the doping equation. Whereas n and delta p will depend both on time and position. Tau n and tau p is given as time between recombination events. So how much time goes between two recombination events is given by tau n and tau p. So if we plot delta p as a function of time, so at t equals to 0, there is a certain amount delta p naught, and at t equals to infinity it reaches 0. So certain at certain point tau p, it will reach 1 by e of the initial value. That is called your lifetime. So excess minority carrier concentration plays a crucial role. So a light pulse is up. So let's take this example where a light pulse is applied to create excess minority carriers at the center point, which is x equals to 0. So at t and t equals to 0, the excess carrier is delta p naught. So so at this point now there's an excess carrier concentration, but at both left and right there are normal equilibrium carrier concentrations. So now this excess carrier concentration will diffuse both left and right. So if you plot delta p at t equals to 0, there is an excess of x. There is a certain value at x equals to 0 and 0 excess carriers, both left and right of x equals to 0. So if you do del of delta p by del t, it is given as dp delta del square delta p by del x square. So first derivative with respect to time and second derivative with respect to position. So recombination process del of delta p by delta t is proportional to your minus delta p excess carrier concentration, which is equal to minus delta p by del t, tau p, which is a minority carrier concentration lifetime. So you can plot versus time as delta p equals to delta p naught exponential of minus t by tau. So which will be this plot. So this will be the equations that you will get. Del of delta p by delta t, del del of delta p by del t is equal to dp d squared del square delta p by del x square minus of del P by tau P plus Gp. So this is the diffusion rate, this is the recombination rate, and this is the generation rate. Similarly, for if electrons are magnetic carriers, but this condition is only valid for low level injection, where your delta P is less than N naught, and delta and it is greater than P naught. So it is much higher than your minority carrier in equilibrium minority carrier concentration, but also much lower than your majority carrier concentration at equilibrium. If your delta P is comparable to N naught or larger than N naught, it is called high level injection. So let's take first case, which is steady state uniform generation. So since it's uniform generation, there won't be any spatial difference in your carrier concentrations. Everywhere the generation of carriers will be same. So, so since there is no change in carrier concentration across the semiconductor, you won't have any diffusion. So your diffusion term will become zero. Similarly, it's steady state. So with so there won't be any change in the in carrier concentration with time. So your time variation will also be zero. So now you only have two terms, recombination term and generation term. So then your recombination rate. So this equation will then become delta P equals to Gp tau P. So let's say your Gp is given as 10 power 17 per centimeter cube per second, and tau P is given as your 10 power minus 6 seconds. So you multiply it, your delta P will then be 10 power 11 per centimeter cube. So you will have a net excess carrier concentration of 10 per 11 per centimeter cube minority carrier concentration, and this is uniform across space and across position as well as time because of steady state and uniform. So this is the simplest case. And now we take another case which is steady state but at large very long sample. So what is a long sample? A long sample is a sample where long sample is a sample where the length is much higher than your diffusion length as well as absorption length. So the light that you are shining is not getting absorbed everywhere, it is only getting absorbed at the initial range. Your length of the semiconductor is much larger than that. So, so we assume that only the initial at x equal to 0 you have carrier concentration, and for the rest of the semiconductor there is no there is no generation of carriers. So again you are given steady state. So again the variation with time is 0, but this time there will be a variation with position because only at x equals to 0 you have excess carrier concentration at all and everywhere else there is no excess carrier concentration initially. So all photons are absorbed at x equals to 0. So inside there is no generation. So inside your Gp is also 0. So now you have the terms recombination term and the diffusion term. So now if you see, it will become del square delta P by del x square equal to delta P by tau P dP tau P. So dP tau P is then written as your L square. So L is your diffusion length. Diffusion length LP is square root of dP tau P. So then this if you solve this, if you solve this equation, you will get delta p equals to a exponential minus x by lp plus b exponential x by lp. But as x approaches infinity, we know that delta p will be 0. So this b term will be 0. Only this a term will be there. Delta p equals to a exponential minus x by lp. And so from previous question, we know that at x equals to 0, the delta p is 10 power 11 per centimeter cube. So that you can put here. So delta p of x is 10 is to power 11 exponential minus x by lp. And lp also you can calculate from the given values. It comes around 30 microns. So lp is the value at which this delta p of x becomes 1 by 1 by e term, 1 by e of the initial value, which is point 0.3 of the initial value, which comes around 30 microns from the given. So next case, you have transient case, but there is no spatial variation. So and no generation. So you shine the light at the initial value at initial time, and then you turned it off at t equals to 0. So there is an excess carrier concentration at t equals to 0, but there is no more generation. So, but for t less than 0, we consider it was when the light was on, it was we consider that to be steady state, and there we had calculated from previous questions, we had the values 10 per 11 per centimeter cube. And for later values, gp is, so now for t greater than 0, gp is 0 because light is turned off. So gp is 0 and there is no spatial variation, so there is no diffusion. So this term is also 0. So for t greater than 0, you have only two terms, this term and this term. So you have del. So it will becomes del of delta p by del t equals to minus delta p by tau p. So if you solve this, it becomes delta p equals to delta p naught exponential minus t by tau p. And delta p naught you had 10 raised to power 11 per centimeter cube. So that you can plot here. And tau p you have been given as 10 raised to power minus 6 seconds or 1 microsecond. So that you can plot on the plot itself. So you can see tau p is the value at which this value becomes 1 by e or 0.3 times of the initial value. So minority carrier lifetimes. Determine the behavior of excess carriers as a function of time. Assume that the excess carriers have been generated uniformly in a semiconductor concentration of delta and not to 10 power 15 per centimeter cube. The forcing function generating the excess carriers turns off at t equals to 0. Assuming the excess carrier lifetime is tau n naught equals to 10 to the minus 6 seconds, determine delta nt for t greater than 0, which is the question similar to the previous question. So it will just be delta n equals to 10 power 15 exponential minus t divided by 10 power minus 6. So generally the excess minority carrier lifetimes will be given in terms of in the microsecond range. So this is how it looks. It will look for. So you generated a, so in the question that we had studied, so we had generated excess of carriers in the middle region, and then we had let it, then we had turned off the light and let it diffuse over time. So you can see this excess carriers will then diffuse both left and right in a bell-shaped curve. So the value at the center will be coming down, and the spread will keep increasing, such that at infinity it will become a flat line again. So this graph shows how the concentration is changing with time and with position. Next we come to quasi Fermi levels. So the quasi Fermi levels is given as, so we have the equation n naught equals to ni exponential ef minus ei by kt, and p naught equals to ni exponential ei minus ef by kt. So if we take n naught 10 power 15, p equals to 10 power 5, then our ef will come out to be around zero point 0.3. So this is the equilibrium case where delta n and delta p are 0. So ef by ei equals to kt ln n naught by ni, which comes out to be zero point 0.3 ev. So at equilibrium, this ef e captures the chiral concentration completely. But what happens when in non-equilibrium case, where your n and p are not equal to ni square? So there, this one single ef value can't give you both n and as well as p values. You will need two different levels. These are called EFN and EFP, and these are called quasi Fermi levels, one for electron and one for hole. So for electron, it will become n equals to ni exponential EFN by EI by KT, and for P, it will be ni exponential EI minus EFP by KT. So as n naught goes to n, your EF goes to EFN. As P naught goes to P, your EF goes to EFP. So let's say your delta n and delta P are now 10 to the power 17. So earlier we had calculated delta, earlier for delta n equilibrium case, delta n and delta P were 0. So your EFN and EFP were equals to EF. But now it's 10 to the power 17. So your n is 10 to the power 15 plus 10 to the power 17, which is approximately 10 to the power 17. Your P is 10 to the power 5 plus 10 to the power 17, which is approximately equal to 10 to the power 17. So EFN minus, then if you calculate EFN minus EI, which is KT ln n by Ni, that comes out around to be 0.42 eV. Similarly, EI minus EFP comes out to be around 0.42 eV. So your EFN is 0.42 eV above the mid gap, and your EFP is 0.42 eV below the mid gap. So this was your Fermi level at equilibrium, and these are your new quasi Fermi levels for this injection. So one thing you will notice, we always say delta n equals to delta p, because we are talking about electron hole pair generation. So when you are generating electron hole pairs, you are generating both electrons and holes at the same rate. So for electron hole pair generation, both your delta n and delta p will be equal. Excess holes and excess electrons will be equal because you are generating electron hole pairs. If you are just injecting electrons and not holes, then your delta n and delta p will be different values. Another example where we take low level injection where delta n equals to delta p equals to 10 raised to the power 10. So your n remains 10 raised to the power 15 and your p becomes 10 raised to the power 10. Now if you calculate EFN, it comes around zero point 0.3, it is 0.3 EV, and for EFP it comes around 0. So so in this case your EFN is same as your earlier EF, but your EFP is now at mid gap value. Now if you take 10 raised to the power 7, then you will have EFN will remain again 0.3, but EFP will become minus 0.1. EFP will become 0.18. So this will be your EFP for delta P equals to 10 raised to the power 7. So, so from this you can say that as delta N increases, EFN moves closer to EC. As delta P increases, EFP moves closer to EV. And as sample approaches equilibrium, EFN and EFP approach EF. So minority carrier diffusion length in band diagram. So at x equal to 0, you have generation. For remainder, you don't have any generation. So from earlier, we had calculated this to be delta p of x equals to delta p naught exponential minus x by LP. So you can say that x as as delta n approaches 0, delta p will approach also 0. Again, this is due to recombination. So both the delta n and delta p will reduce at the same rate. So EFN will approach EF and EFP will also approach EF. So from earlier we had seen that at 10 raised to the power 10, EFN is equal to EF and EFP is equal to EI. So as x approaches infinity, sample will approach equilibrium. Hence EFN and EFP should move towards EF. So initially you have delta P naught equals 10 to the power 17. So for that we had calculated 0.42 EVs above and below. So your EFN is like this and your EFP goes like this. So you can see your EFN goes like this and your EFP goes like this. So these are not straight lines. These are curved exponential curves. So these are exponential decays, but in the band diagram they can be represented by a straight line due to the term due to this log term. So EI minus EFP equals to KT ln P by NI. So P you can change to P naught plus delta P naught exponential minus L by LP by Ni. If we assume delta P is greater than P naught, then it becomes KT ln delta P naught by Ni into exponential minus X by LP. You take this term out, it comes out to be KT ln delta P naught by Ni, which is a constant term, minus KT by ln X. So this is a linear equation. So hence these are these can be represented, although they are exponential decays, here they are represented as straight lines. Next is quasi Fermi level and currents in non-equilibrium. So we had studied that Jn equals to Qn Qp mu p uh, epsilon minus Q dp del p. So this is a drift term and this is a diffusion term. When p is given as ni exponential ei minus efp by kt. So del p is equal to dp by dx, which is ni exponential ei minus efp by kt into 1 by kt dei by dx minus defp by dx. And we know we know electric field is 1 by q dei by dx. So this term becomes pq by kt electric field minus p by kt defp by dx. So hence your total whole current becomes q qp mu p ep minus qp dp q by kt elect e plus p q by kt dp del of efp. So we know that mobility is given as dp into q by kt. So this is mobility again. So this term and this term will cancel out, and the only term will remain is p into q by kt dp del, delta efp. And again q by kt dp can be written as mu p. So you will have jp equals to p mu p delta of efp, and jn is n mu, then jn is n mu n delta of efn. So the gradients of the quasi Fermi levels can directly give you the current density. Next we will be studying the for, for manufacture of electronics. So we start from the raw material, which is sand. So sand is your SiO2. From there we develop metallic grade sand, which is called EGS. From there we develop electronics grade silicon, metallurgical grade silicon, which is MGS. From there we develop electronics grade silicon, which is EGS. And from electronic grade silicon we develop the silicon ingot. And from this silicon ingot then we cut it and make our silicon wafers, on which we make our electronic devices. So if you go to this link, this will show you how from how starting from sand we get our semiconductor devices. So the whole process of chip manufacturing by Infineon. So this was the recap for this week. Now we will do some practice questions, which will be helpful in your assignments and your exams. If you know the answer, you can say out the answer or you can write in the chat. First, according to the Einstein relation, for any semiconductor, the ratio of diffusion constant to mobility of carriers depends upon the type of the semiconductor, varies with the lifetime of the semiconductor, is a universal constant, depends upon the temperature of the semiconductor. That is correct. The answer is D, depends upon the temperature of the semiconductor. So the formula is D by mu equals to KT by Q. So you can see, so K and Q are universal constants, Boltzmann constant and Coulomb's constant. But T, T is the varying term variable. So the correct answer is depends upon temperature of the semiconductor. Next question. If the mobility of minority carriers in an n-type semiconductor is 480 centimeter square per volt seconds, then what is the diffusion length of these minority carriers within the semiconductor? Assuming minor carrier lifetime is 10 microseconds. So the formula you have to use the from mobility you will have to calculate the diffusion constant, and from diffusion constant and the minority carrier lifetime you have to calculate the diffusion length. Uh, Temperature you can take as 300 Kelvin. If we have not given temperature, you assume it to be 300 Kelvin. That is correct. The correct answer is C, 101.5 microns. So your L diffusion length is given as square root of diffusion constant and carrier lifetime, and the diffusion constant is then given as your mobility into kT by Q. So for 300 Kelvin, your kT by Q is 0.0259, 0.0259 volts. So you multiply 480 into 0.0259 into 10 is to 10 microsecond, which is 10 is to 10 to minus 6. And when you solve it, you will get 101.5 microns. Next question. Assume the donor concentration in an n-type semiconductor at T equals to 300 Kelvin is given by nd of x equals to 10 raised to power 16 e power minus x by L, where L equals to 2 into 10 raised to power minus 2 centimeter. Determine the induced electric field in volt per centimeter at x equals to 1 into 10 to minus 4 centimeter. So this is the question that we had seen in the recap lecture. Options are 4.13 volt per centimeter, 1.29 volt per centimeter, 2.45 volt per centimeter, 3 volts per centimeter. The correct answer is 1.29 1.29 volt per centimeter. So you know EF minus EI is given as KT ln n by Ni, and instead of n you can write Nd. So you will get EF minus EI equals to KT ln Nd by Ni. So if you take the derivative of that, so in equilibrium condition, your del EF by del X will be 0 because your EF is constant in under equilibrium. So and you will have then minus EI by EX equals to KT del, del of ln Nd by Ni by del X. So if you put Nd is 10 power 16 E minus X by L by Ni, which is 10 power 10, you take Ni is 10 power 10, you so this 10 power 16 by 10 power 10 will become 10 power 6. So that will, so ln so that will come out to be ln 10 power 6 outside that, and then this term becomes ln of E minus X by L. This term becomes minus X by L. So it will become ln 10 power 6 into KT minus minus X by L into KT, and then your electric field is given as 1 by Q dEI by dx. So then you so that will become KT by Q ln 10 power 6 minus KT by Q minus X by minus KT by Q X by L, and for 300 Kelvin your KT by Q is then 0.0259. So if you put X equals to 1 into 10 power minus 4 and L equals to 2 into 10 power minus 2, I can solve for your built-in electric field from there. In an n-type semiconductor bar, there is an increase in electron concentration from left to right, and an electric field exists beyond pointing to the left. If we double the electron concentration everywhere, what will happen to the diffusion current and drift current? Diffusion current doubles and drift no changes. Both doubles, diffusion current doubles and diffusion no changes. No change in both currents. That is correct. Both diffusion and drift current will double because so both depend on, so your drift current is NQ mu E. So if you double N, your drift current doubles, and diffusion current is dq dn by dx. Here also if you double the N, your dn by dx will also double, and your diffusion current will also double. Next is consider a hypothetical energy band diagram as shown in figure 1. Sketch the electric field as a function of x is best described by. So this is your hypothetical band diagram, and these are the four electric field versus position diagrams sketches. Which one is the correct one? That is correct. The answer is C. That that is A. So this is the correct one because your electric field is proportional to D slope of EC by x, so which is negative here and negative here and 0 in the constant 0 in the middle, so it's negative 0 negative. So for next four questions, to consider the parameters q equals to 1.6 into 10 to the minus 19 coulomb, mobility of electron equals to 1200 centimeter square per volt second, kT by q you assume as 26 millivolts, n you take n is electron concentration, you take as 2 into 10 to the 15 per centimeter cube, electric field is given as 400 volt per centimeter, and del n by del x is given as 2 into 10 to the 20 per centimeter cube. From here, calculate the drift current density. 120.5 angstrom per centimeter square, 1.28 ampere per centimeter square, 1.28 ampere per centimeter square, 153.6 ampere per centimeter square, 200 amperes per centimeter square. What is your doubt? Anything you are not given, you consider as zero. Yeah, so this value n equals to 2 into 10 is by 15 per centimeter cube is given at x equals to 0. So all these values you consider at x equals to 0. Your n value, your e value, mobility will be constant. So e also you consider it to be at x equals to 0. And that is correct. The answer will be C, 153.6 ampere per centimeter square. So drift current is given as n q mu and e, and all the values are given in the question. So you just put those and you get 153 ampere per centimeter square. Next is calculate the diffusion coefficient Bn. 31.2 centimeter square per second, 20 centimeter square per second, 3.56 centimeter square per second, 15.8 centimeter square per second. That is correct. Your dn will be 31.2 centimeter square per second. So dn is mu n kt by q. So mu n is 1200, kt by q given as 26 millivolts. So multiply, you will get 31.2. Next is calculate the diffusion current density. 998.4 ampere per centimeter square, 9.984 ampere per centimeter square, minus 998.4 ampere per centimeter square, minus 9.984 ampere per centimeter square. Actually, that is wrong. It will be minus 998.4. So diffusion current is given as minus Q dN del N by del X. So there is a negative sign here. So it will be minus 998 ampere per centimeter square, not plus. So next question. Calculate the total current density. 854.5 ampere per centimeter square, minus 700 ampere per centimeter square, minus 845.4 ampere per centimeter square, minus 743.6 ampere per centimeter square. That is correct. It will be minus 845.4 ampere per centimeter square. So total current is drift current plus diffusion current. Your drift current is 150. Your diffusion current is minus 998. So you subtract it, you will get minus 845. So next question. In a semiconductor, the magnetic carrier concentration profile is given by the formula delta Nx equals to delta N naught exponential minus x by L. Which of the following statement is true? A longer diffusion length L results in a slower decrease in minority carrier concentration with distance. A longer diffusion length L results in a faster decrease in minority carrier concentration with distance. Both are true, none are true. Statement 1 is true, statement 2 is true. That is correct. Statement 1 is correct. So if you have your L is larger, so the this exponential term will reduce less by lesser amount your diffusion. So it will reach 1 by E at a larger distance. Hence the decrease is slower. And statement 2 is just the opposite of statement 1, so only one of them can be correct. So that is all I had for today. Thank you for attending the session. If you have any doubts, you can ask. If you don't have any doubts, you can leave the session. Thank you.